To make an AI agent useful on-chain, it needs a reliable way to read blockchain data. RPC Endpoints and Web3 SDKs provide that bridge, letting apps query balances, blocks, transactions, tokens, and contract state in real time. So far, we've moved from agent basics into blockchain essentials, wallets, keys, and signing. Now we add the data access layer, so an agent can check balances, transactions, blocks, and contract state before deciding what to do. AI agents usually do not read a blockchain by connecting to the chain directly. Instead, they ask a node through an RPC endpoint. Think of RPC as the agent's query language for on-chain context. Calls like eth_get_balance, eth_call, eth_get_logs, and transaction receipt lookup return the facts the agent needs: balances, contract state, events, blocks, and confirmations. If that access is slow, stale, or unreliable, the agent's reasoning becomes unreliable too. An RPC endpoint is more than just a URL. The URL tells your app where to send requests, but the network settings tell it which chain it is talking to. Always configure the network name, chain ID, RPC URL, currency symbol, and Explorer link explicitly. API keys usually belong in environment variables. If these values are wrong, your agent may read the wrong chain or prepare transactions that fail. Public RPCs are useful when you're learning or testing quickly. They cost nothing and require almost no setup, but they can throttle requests, go down unexpectedly, or lack historical data. Paid providers add the infrastructure production agents need: higher throughput, monitoring, archive access, support, and more predictable latency. The trade-off is cost versus reliability. For serious agents, use a trusted provider, track usage, and plan failover. Blockchain agents can generate heavy RPC traffic, especially when they track wallets, events, and prices continuously. A robust client layer protects the agent before infrastructure problems turn into bad decisions. It batches repeated reads, caches data that does not need second-by-second freshness, and retries failed calls with exponential backoff. If the primary endpoint slows down, hits a limit, or returns errors, traffic should fail over automatically, while monitoring alerts the team to rising latency. Web3 libraries act as the adapter layer between your code and blockchain nodes. In Python, web3.py is the standard starting point. In JavaScript and TypeScript, ethers.js, VM, and web3.js are common choices. These libraries turn raw JSON RPC into cleaner actions, like connecting to a provider, reading balances, calling contracts, signing transactions, and decoding events. Provider SDKs can add higher-level features, such as NFT data, token metadata, simulations, and indexed queries. With web3.py, a Python process talks to an EVM chain through an RPC endpoint. Start by loading the RPC URL from environment variables, then create a Web3 HTTP provider. Before an agent or backend workflow depends on it, verify the connection with isConnected. Once connected, the same client can read balances, latest block numbers, transactions, and contract state. That simple pattern makes blockchain access feel like a normal Python service dependency. In JavaScript, the connection pattern is similar. Create an RPC-backed object, then use it to read chain data. With Ethers, that object is usually a JSON PPP provider, and contracts or wallets build on top of it. With VM, you create a typed public client using a chain and HTTP transport. Both approaches work in browsers or Node.js, but production code should keep network configuration explicit and typed. Native chain reads answer the first operational questions an agent has. Does this wallet have enough base asset to act? What is the newest block, and what does it say about timing, gas usage, and included transactions? If a payment or action occurred, the transaction hash lets the agent inspect sender, recipient, value, call data, gas settings, and nonce. Together, these reads support monitoring, payment verification, and decisions about when it is safe to proceed. When an agent sees a transaction hash, it only knows the transaction was submitted. The next step is to poll for the receipt. The receipt shows the execution outcome, success or reverted, along with gas used and the block included. Then inspect the logs, because token transfers and contract events often live there, not in the basic transaction. Finally, count confirmations. For high-value actions, wait until enough blocks build on top before treating the result as final. ERC20 token data works differently from native coin balances because it lives inside the token contract. An agent reads current state with calls like balance off, decimals, symbol, and total supply. The raw numbers are not automatically human-friendly, so decimals tells you how to scale them. Transfers follow a separate path. They are tracked from transfer event logs showing sender, receiver, and amount. Combining state reads and events lets agents build portfolios, verify payments, monitor treasuries, and trigger alerts. To read a contract, your agent combines the contract address with the ABI. The ABI tells the library which functions exist, what inputs they expect, and how results should be decoded. For view or pure functions, the library packages the request and sends it as an eth call to a node. The node simulates the call against current chain state, returns bytes, and the library turns them into a value. No transaction, no gas, no state change. Events are the contract's structured signal layer. An agent can backfill history with eth.get logs, filtering by address, topics, and block range, or listen for new events over WebSockets. A reliable pipeline decodes each log with the ABI, processes history in safe block chunks, removes duplicates, and stores checkpoints. That bookkeeping matters. Providers rate limit large scans, chains can reorganize, and repeated logs happen. Only after those safeguards should events trigger tools, alerts, or workflows. The big idea is simple. Before agents act on-chain, they must read on-chain reliably. RPC endpoints connect them to blockchain data, and SDKs make those reads practical. Strong agents handle limits, retries, failover, caching, confirmations, and checkpoints. Next, we move from observing state to interacting with smart contracts.